Now we intend to start talking about the second part of the nonlinear time series models. So we'll start with bilinear time series models. Bilinear time series models constitute a class of nonlinear models where the linear ARMA model, autoregressive moving average ones, is augmented by the product of R, AR and MA terms. These models are able to generate a wide range of time series patterns, including bursting behavior as observed in stock market bubbles. So this is very important. We want to talk about bursting behavior in stock market bubbles in bilinear time series models. So let's start with specification. Let's consider a ARMA 1-1 model where VT is a structural residual with IID, zero mean sigma square variance disturbance, moving average disturbance. From the first example, values of phi less than 1, so autoregressive parameters if within the unicycle, which are stationary, result in the model exhibiting uniform variation around its unconditional mean. So basically, phi less than 1 means we're talking about stationary models. Now consider the stationary models, what happens is that the variation is generally surrounding its unconditional mean, meaning that we see mean reversion. We don't see explosive behaviors in our stock market variables. Now consider the introduction of a nonlinear term, yt minus 1 and vt minus 1, moving average parameter, which is simply the product of AR1 and MA1 components of the model. That's all, very simple. Well, this is the ARMA portion and this is the nonlinear portion. The additional component is the bilinear term. Okay, the additional component here is a bilinear term, which is the effect of generating a range of interesting nonlinear features that ARMA models cannot generate. Okay, this is interesting, right? So just multiplying autoregressive moving average terms, we have a bilinear term which can generate interesting nonlinear features. So let's start with properties of the bilinear time series model. So let's simulate a t equals 200 observation from bilinear model, and this is given. This figure is given. So 19.8, where we have a bilinear time series, simulated bilinear time series model for different values of gamma, with t is equal to 200 auto AR and MA. So different values for different values of gamma and fixed autoregressive and moving average parameters with different values of gamma generates interesting what should I say bilinear models, right? So exhibit the typical for values gamma equals 0 and gamma equals 0.4. The model exhibits the data exhibits typical pattern of a linear ARMA model. Increasing gamma further causes the model to exhibit bursting and extreme bursting behavior, which is characteristic of stock market self-correcting to shocks, right? Very interesting, right? So for lower gamma values, for lower order gamma values, we have what? For lower order gamma values, we have typical pattern, typical linear ARMA models. This is typical linear ARMA models. But for higher order gamma models, we see bursting behavior, okay, stock market bubbles. So self-correcting, so whenever there is shocks generated that are being self-corrected. Interesting. The specification of the bilinear model is easily extended for longer lags, alternative bilinear product terms and higher dimensions. So we can be easily extended for longer lags, alternative product terms, higher dimensions. An example of a bivariate bilinear model with 2 lags. Simply multiply these autoregressive and moving average parameters for up to 2 lags. The terms, bilinear model terms, yt minus 1 v2 and y1 minus 1 v1, capture alternative types of spillovers that may represent a way to model contagion. Okay, so that captures alternative spillovers, that is a way to represent. So different types of spillovers are being generated to present that are used to present contagion model. Okay, estimation. Now we have specified the model. Let's see how we can estimate this model, right? Estimation, let me save this file. Just give me 1 second. Estimation of a bilinear time series model using a maximum likelihood method requires specifying the conditional log likelihood function. In the case of bilinear model, in where the disturbance term is 0 mean sigma square variance, where the number of lags is p equals q equals 1 and the unknown parameters are theta equals phi, then psi, gamma and sigma square. The conditional log likelihood function for a sample of t equals 1 to t observation is y minus phi yt minus 1 psi vt minus 1 minus gamma yt minus 1 vt minus 1 squared, right? So just simple log likelihood function. This function is maximized with respect to theta using one of the algorithms. Any of the algorithm as an alternative iterative procedure. The Gauss-Newton algorithm discussed in chapter 6 can also be used because the log likelihood function is expressed in terms of sum of squared disturbances, right? So just the log likelihood function. General maximum likelihood estimation technique. Testing. A special case of a bilinear model is the ARMA PQ model. This suggests that the hypothesis testing methods can be used to construct general test of bilinearity. In the case where there is no moving average term, the regression from LM given in chapter 6 is particularly simple to implement. Considering a bilinear model, a test of bilinearity is based on the following hypothesis. Well, gamma equals 0 and gamma not equals 0. To implement the LM test of bilinearity, the steps are as follows. So basically, interesting, if we run this test, we will probably be able to prove if there is bursting or there is no bursting. So if we take a series and if we run this test, if there is bilinearity, then there is bursting behavior. If there is no bilinearity, then there is no bursting behavior. So we can first, what we can do, we can collect a set of data, we can run the test, then we can go on trying to estimate the parameters. So let's rewrite the equation and compute the derivatives. That is step 1, z1 and z2. Evaluate the expression in step 1 under the null. So we have to rewrite the equation and we have to compute the derivative, first order and second order derivative, and we set gamma to 0. If we set the gamma to 0, we are left with this, right? We are left with only these expressions, z1 t, z2 t. Estimate the model under the null by regressing y on yt minus 1 and extract the OLS. First we take this out, regress epsilon on yt minus 1, on these two, and compute r square. So first we know the derivative, then under the null hypothesis we make regression and extract OLS, the square residual, and we regress our model on yt minus 1 and yt minus 1, vt minus 1, and compute r square. From the LS statistics, LM, where t is the sample size and compared with a chi-square distribution, the null hypothesis is rejected for large values of the test statistic because this result implies that the bilinear content. So if we reject a null, that means there is the null hypothesis is rejected for large values of t statistics, right? So basically what we do here, in first stage regression, it implies the bilinear component has been excluded. So basically, what is our null here? Null is bilinear component. There is not bilinear, is bilinear, right? Bilinear component exists. So if we reject the null, that means the bilinearity component exists for higher order test statistics. So that is a very important example where we can simply test with LM test. We do LM test on our bilinearity model, and these are the steps that we would follow. Then we talk about MarkovSwitch model. But let's move into see what are the examples that we are talking about here. So now what we're gonna do is that we're gonna, whatever we learned right now, we're gonna just see bilinear and bilinear testing and we'll probably try to find out if there are shocks or bubbles in the system. So let's simulate a bilinear model. With these is the equation for, and we are given 4 different gamma values, and we will see as gammas increase we see different shocks, and the starting values is y0 and v0 is 0. Our sample size is 300, and then we are going to discard the first 100 observations to remove the initialization. We'll describe the properties of the 4 time series corresponding to each value of gamma. So we'll have 4 different time series for 4 different gammas, right? Indeed we will. And we're gonna simulate the another bilinear model. So here our VT is 0 mean and 1 variance, 0 mean and sigma 1.1 variance. So for gamma equals 0.4, the starting value is y0 and v0. Choose the sample size. We'll have 1100 observations now. We'll have different initial value, and we'll again discard the first 100 observation. We'll estimate the parameters by maximum likelihood estimation. Okay, and we'll use these results for bilinearity testing using LR, WORLD, and LM, where the property of gamma is 0. So let's see, it's gonna be fun. First bilinear equation, right? Now there are 2 scenarios here. We are doing obviously we are doing random number generation. You might have stock market data on which you want to apply this, whatever we are gonna start. So first, this function is for simulation. If you have data already, you might not need to simulate your data. However, let us simulate our data and we see how this goes. We have unknown parameters, which is t, phi, theta, and gamma, right? And we actually are allowing our system to generate the number for us to. So for I equals 2, so these are actually, these are inputs, I, t, phi, theta, gamma, and this is our equation, phi y minus 1 ui, theta ui minus 1, and the gamma equation. We have the equation. Now let's put this into a loop. We want to generate y given these numbers or these values, with our loop. I equals 2 plus t plus 100. Obviously it will go up to, like, we have 300 observations, it will go up to 300 plus 100. Then we will just discard 101 from the end, like that. Very simple. And you can always match the dimension to see if you have correct amount of dimension. Now it needs you to put zeros, and obviously this is an important part that we missed. Random number or residual is randomly generated, 100 rows, 1 column, and so we'll have R norm, not only random but R norm, 100 rows, 1 column, based on which our y is generated and y will be stored here. So basically this is a bilinear function with this equation, that's all, nothing else. Let's see what follows from here. So this system will return y. It will give us a data set. You might have a data set and you don't need to do this in that case. So you have 200 parameter, t equals 200 observations. Okay, so we have t equals 200 observations, and let's simulate the model. For gamma 0, this is our model. For gamma 0.4, this is our model. So basically we are simulating the model for different gammas here, right? There is the thing is, you might be able to introduce this gamma term with whatever structural variable you have with you. You can simply, I think, the variable that you have with phi's and theta's already, you can simply introduce the gamma term there in the equation estimation. So bilinear y1 is with 0, this is the first bilinear model, 0.4 second bilinear model, 3.8 third, and 4 fourth. So we're just generating this bilinear models and graph. That is very, very simple, right? And when we generate the graph, because we're putting y against t, and every time with different gammas, that's all. So we see that the graph we have just seen, some will be generating, the first two will be generating a linear model, the second two will capture the bars, okay, the bubbles, and that is how from random numbers we can generate a bubble. The question is, from given data set, how we can generate bubbles. We might need to introduce the non-linearity term, identifying our equation for autoregressive and moving average parameters. We might need to introduce different, so the first, before this we need to do some ARMA, autoregressive and moving average calculations on our given vector. So you have two steps here. First, you specify the equation on your data. You have the autoregressive and moving average parameters. Then you just pass in gamma, specifying the equation one more time. That's all. So very simple. Then comes bilinearity test, and this equation asks us to check if there is bilinearity in the model or not. And bilinearity, for bilinearity test, we will do what? We will do log likelihood functions. We know the log likelihood function, we just studied that. So we have two log likelihood functions, unrestricted and restricted, right? So the first log likelihood function, which is unrestricted, we have the residual equation, the whole residual equation. Now first define the equation, then put that into the loop, the 2 to number of observations. Now because Vt will need zeros to set against Vt, and we need to specify number of observations, which is length of y. So go the other way around, start with the equation, go the other way around, it will be easier for you to set this. And you see the dimensions, because it's the dimensions will be different, so we'll trim one, because we need to remove the initialization. This is the level effect, and well, this system will take in b and y, it will take cb and it will take y, and it will estimate log likelihood function. So variance is mean variance square, z is the standardization, and then log likelihood function is this is the log likelihood function, just as before. Z square, we are just simplifying the residual divided by the variance squared, or z squared, that's all, taking the mean, a very shortcut way to do that, and return log likelihood function. Then comes restricted. In restricted, do the equation again, just remove the non-linearity part, and that becomes unrestricted log likelihood function, and very simple. Then we go into talking about our model, and we simulate data. We take well, t 1000 time, y is 0, t plus 100 1, or residual is simulated with square root of 0.1 variance, given variance. And this is the equation that we use to generate, because in our question, yeah, this is the equation that we are where lambda is also 4, not only 0.4, your gamma is also 0.4. So to generate our nonlinear equation, and then we put that in for loop, and then we see it requires what, v, so randomly generate v, and then what else, we need to store it, so store, and all these requires how many times this will happen, loop will happen till 1000 times. So you see, and then we adjust for the last 100. So we have initialized, this is the random number generation, this is the simulation phase, only the simulation phase. Now we have y, and why don't we just estimate the unrestricted model with y, right? We estimate the unrestricted model for all the parameters. Okay, beautiful. If you have y, you can estimate a model with this changing, log likelihood. With the log likelihood function, you can estimate any parameters and setting an equation. You can estimate any parameters and see, for higher order gammas, you can estimate it multiple times to see for higher order gammas you are capturing bubbles. So this is another way. Instead of doing autoregressive moving average parameters separately, you just run the maximum likelihood function parameter, and you devise your equation already. Then you estimate your parameter. That's all. You don't have to draw data. You just estimate your theta parameters, and your theta parameters estimation, meaning you estimate everything, phi, autoregressive moving average, then you put those in the equation that you want to do, and it should give you the nonlinear model. So we estimate it, and we have VC and standard error, log likelihood function, standard errors. So this is estimation of the unrestricted model, full with nonlinear parameter. This is the estimation of the restricted model, and the difference is giving you the LR test. We also have word test, which is theta 1 3, right? What is the third parameter that we are estimating? Well, it depends on the third parameter. Theta 1 3 is our third parameter. Let's see which one is our third parameter. So we have by, you have by, not sure. So anyway, then wall test, LM test is fine enough, you don't need to do many tests, but yeah, sure, let's have a look. LR test and wall test, I think is very mean. I think is the mean. Phi, we have phi, you have gamma, we have mean, you have variance. Yes, mean divided by variance covariance 3 by 3. So we have p-value of wall test, and then we have LM test. Okay, and the first stage regression of LM test is, so the first stage regression for LM test is for our combined days ones and the lag ones and the lag element and level element of x, then simply number of variables, we do the v residual will be received from the regression. Second stage regression is now level element, and we are talking about v, so the equation changes now, right? lag element, level element is what it is. Then lag elements. This is the lag element 0, 1, 0, v01. Lag element of vt minus 1. Level element for all other, variables. The first equation, the second equation variables. Second equation variable has the bilinear term, so v will come into play here. And then we have the other residual, and then we do r square, and then we do LM test. That's all. So this will help us identify if there is bilinear term or not. If our LM is greater than chi-square distribution, then we have we reject the null of gamma 0. That means we have bilinear, otherwise so this is very simple. We are trying to find in this test if in our model we have bilinear bilinearity or not. So basically, if you combine this test, you can do two stuff. First stuff is if given data, if not simulated data, you can first try and test that actually do you have any shocks in your stock market data that is given to you. By doing testing, if there is something that is bilinear, so if your hypothesis testing supportive of existence of a bilinearity in the model, then well, you can proceed with the equation. Another thing is that now you need to use log likelihood function right here, because in bilinearity test you need to have the equation with you that generates your data, but your data is already generated and you don't need to do any more simulation. In that case, what can you do? You can simply, with maximum likelihood estimation, you can simply estimate the parameters phi, psi and everything, jack them in with a nonlinearity term, and that should be able to when you draw the graph with different gamma values against the parameters that you're initializing your analysis with. What happens if you do that? Then you're probably concentrating out the bubbles. So with different levels of gamma or introduction of nonlinearity, you see that there are different types of bubbles in the system, and you can select on one type of bubble and continue with your analysis, which is quite good. So this is bilinearity test and bilinear model, where we simulate data with a simulation technique and with a given equation, which basically is something addition. We need to have phi and psi values not given to us but generated somehow to us. So this is important that we also revise linearity model before moving into this. Combining the codes will give you a new type of analysis. And then we'll talk about we have seen that. Now we are going to talk about the next MarkovSwitch model. So now we have in the last recording we stopped talking about in bilinear models, and we have seen how beautiful it is to explain econometrics with artificial neural networks, and how we can use bilinear non-stationary time series models to explain bubbles in different exchange markets or equity markets. Now we are gonna delve deeper into this into similar concept, but with a very popular method called MarkovSwitch Model, which allows us to split our data into two different regions and focus or concentrate out specific information from these separate or different regions based on nonlinear stationary time series models. The Markov switching model is widely used to model nonlinearities in economic and financial process. Examples include business cycles, term structure of interest rates, exchange rates, and stock returns. And business cycle factor models. This model has much in common with the threshold time series models discussed previously, the TAR models, if you can recall. We had 4 types: TAR, star, SETAR, and we know how it was important for us to look into with iteration. We tried to see in our threshold models that as the power of it changes, basically as the power of the model changes, the models tend to converge to linear models. Now, except in these current models or in Markov switch models, switching is deterministic, whereas in the Markov, so in threshold models switching is deterministic, whereas in the Markov switch model the switching was stochastic. So this time we might have to rely on random number generation. This model is also similar to the latent factor models analyzed earlier, Kalman filter algorithm, with the minor difference that the factor is discrete in the present context. Let omega t represent a stochastic weighing variable that switches between regimes according to regime 1, omega being 1 for regime 1 and 0 for regime 2. So previously in threshold models we determined or we fixed where how much data will be split into 2 different regimes. This is possible that in this model we might have allow the system to decide that for us. Unlike the threshold time series models, whereas the weighing function is identified by expressing it in terms of lagged observed variables, omega here, the weighing function is not observable. Moreover, weighing is binary for the Markov switch model compared to the weighing function in the threshold models, where in general it takes on intermediate values in the unit circle. So basically what we are saying that in threshold models, in generally the weighing function was located within 0 to 1 and numbers were generated in between or that range, whereas in Markov switch model this weighing will be 0 or 1, so it will be largely binary in this case. A Markov switch model for y, a dependent variable, is specified as, so the first equation is alpha plus beta omega t plus ut. Now sigma square is gamma plus delta omega t. Variance, residual is in 0, mean and sigma square variance, where we have p and q, and the probability of weighing being 1 is p, probability of weighing being 0 is q. That's all. So our unknown parameters are alpha, beta, gamma, delta, p and q, and our residual is heteroscedastic disturbance terms in regime. So we expect that our residual will change across time with regimes. In regime 1 the mean is alpha, obviously, because residual mean is 0. So in regime 1 the mean is alpha plus beta with variance gamma plus delta, while in regime 2, when is omega, the weighing function is 0, the mean is alpha and the variance is gamma only. The weighing variable omega is specified in terms of parameters p and q, which represent the conditional probabilities of staying in each regime. So basically the binary number is conditional upon the lag of weighing function or the lag of the dependent variable. So that's why we're saying in both cases is conditional probability that we are talking about. An important extension if the model is to allow for p lags by writing the first equation. So up until these we are talking about what we had before just mentioned. Then we extend the model by allowing as many autoregressive terms as we want, p lags, phi1 residual, and so we solve this for the residual t minus a minus alpha minus beta weighing function t minus a, because p is conditional upon the lag of weighing function. Further extension consists of specifying yt, the dependent variable, as a vector of variables and allowing for time varying conditional probabilities p and q by expressing these probabilities as a function of explanatory variables, right? So basically we are saying that if we want to extend this current specification, we can allow y being a vector of different variables, and we can also allow p and q to express themselves as function of explanatory variables or x. So they will attach them to exogenous variables, that's all. We will talk about this extension in exercise 6. So p and q will coincide in exogenous variables. Estimation of the model by maximum likelihood requires the joint conditional distribution, which is complicated by the fact that omega is not observed, it's a binary number. To circumvent this problem, it is necessary to integrate, or more correctly sum out omega t. So we need to correctly sum out omega t, that's something we need to remember, thereby expressing the likelihood just in terms of the observed variable y. So because in estimation we are using joint conditional probability, and because omega is not observable, we need to sum out omega, and we need to express the likelihood function in terms of yt, the dependent variable. A similar strategy is adopted in the stochastic frontier models in chapter 6. As omega is binary, this strategy is relatively straightforward, as the summation involves just two terms. Beautiful, right? So we need to sum out omega in the maximum likelihood estimation and express our estimation with yt. So up until now what we learned that a MarkovSwitch model, how it looks, what is the structure of the MarkovSwitch model, and we have more unknown parameters now, p and q, which are conditional probabilities of the weighing function that actually conditions upon the lag of the weighing function, and basically they're stochastic, so they are randomly generated. We have also learned that we can extend that equation by the main equation by including as many autoregressive parameters as we want very easily, and we can also further this by including elements in yt, dependent variable, whereas omega t will coincide in exogenous variable. However, the estimation technique is a bit complicated in this case, because omega t, or the exogenous variable, is not observable, it's not observed, and so we need to express the maximum likelihood estimation on dependent on yt, and hence we need to sum out omega t from that process. This is a straightforward system because it just requires two terms. To demonstrate the mechanics of the approach, conditioning on So the mechanics of the approach that conditions on the lags is initially suppressed to simplify the notation. The conditioning is initially suppressed, the lags are initially suppressed to simplify this notation. From the rules of probability, the marginal distribution is now, well, omega t. So we are suppressing the lags and rewriting the previous well, probabilities p and q. We are summing p and q in this as function of yt. When we sum p and q, but how do we express them? Basically, this is function of y conditional upon omega t, function of well, function of y conditional upon omega t for different binaries, for 1 and for 0. That's all. Which shows that the marginal is obtained by summing over the joint distribution So we are obtaining the marginal distribution by summing over the joint distribution, which in turn is expressed in terms of the product of the marginal and conditional distributions, right? So the marginal and the conditional distributions are being well, multiplied this time. This expression is re-expressed by making condition on past value. So this time we just suppressed the dependent variables. Now we're gonna, well, remove that suppression. So conditional, the function is yt conditional upon the lags, where weighing function 1 omega 1 conditional upon the lags from here, right? 1 t conditional upon t minus 1, whereas function of 1 plus omega naught t conditional upon t minus 1, and the function naught t conditional upon t minus 1. So where this is, well, yt conditional upon t minus lag, and the function is conditional upon is lags. So we suppressed and then we just re-expressed. That's all, no big deal. Represents the, well, this time this equation represents the likelihood function. This is the likelihood function. Basically we have two likelihood functions that are multiplied with omegas now, weighing functions. At time t, which excludes omega by construction with the weights at time t. Now the likelihood function at time t, this expresses the likelihood function at time t which excludes omega by construction with the weights at time t, now expressed in terms of conditional probabilities, which are implicit functions of all previous lags of yt. Well, we'll see what they mean in the real application. They're trying to say that we're excluding the weights at time t, which is expressed in terms of conditional probabilities. Now this likelihood function has the form of mixture distribution with weights that vary over the sample. So we basically summed them over, and the actual function is split into summation of two weighing functions, and we are concentrating out somehow, we'll see, to evaluate the likelihood function. The equation in 19.23, in equation 19.22, to evaluate the likelihood function in the first equation. From equation, the likelihood function is now 1 by root over twice pi. Instead of sigma square, we have gamma plus delta, exponential of the residual divided by 2 gamma plus delta. So wow, it's very simple. Basically the whole equation relied on, for the first one, on gamma, on weighing function being 1, then weighing function being 0 means one term vanishes, so delta would actually vanish, and with that we have y minus alpha, because beta is associated with delta, isn't it? Yeah, beta is associated with the delta. So just keeping that in mind, these are our functions to derive expression for the different weighing functions from equation 19.23, which is this. Now we have these functions and we need to derive expressions for the omegas. So basically we have the functions, so we might need to add them up, and we need to express these omegas as well. So these two are important, and omega, which is conditional, binary 1 conditional upon the lags, is omega 1 multiplied to function 1, omega 1 function 1, omega naught function naught. So denominator is same, omega naught function naught, right? The question is with numerator. The numerator will shift, which was omega 1 function 1. So function 1 and function naught is coming from here, and omega naught. Using the definition of P and Q in equation 19.22, it follows that we can write the omegas, the back propagation or moving forward of omegas with P, Q, 1 minus Q, 1 minus P. So this is the matrix, okay, where the non-diagonal elements are 1 minus Q or 1 minus P, and diagonal elements are P and Q. There is just one question hovering over my mind, which is if I have values on omega, only then I can determine. So if I have values of omega on lag terms, on terms of lags, lagged omegas, then it will help me to find out the current omegas. That's all. So we have different functions, and now we have to specify omegas from lagged omegas. That allows us to find omega 1 and omega naught, and then we jack them together, right? That's the idea. So for a sample of t equals 1 to t observations, the log likelihood function is now the log likelihood function is omega 1 and omega naught. That's all. So basically we have multiple equations. We have to first determine a function with omega 1, then we have to determine a function of omega naught, then we have the terms omega 1 and omega naught themselves, which gives us a fraction equation where the denominator is same for both, whereas the numerator changes. We jack them all together in the log likelihood function. So where omega 1 and omega omega and phi are defined in these earlier equations respectively. This function is maximized with respect to theta using the iterative algorithm presented. So fine, at t equals 1, it is necessary to be able to evaluate omega 1 and omega naught, which are set of equations to their respective. Okay, at t equals 1, it is necessary to be able to evaluate omega 1 and omega naught, which are set equal to their respective stationary probabilities, right? So omega 1 is 1 minus q, 1 plus p, 1 minus q remains exactly the same numerator. Denominator is 1 minus pq. For omega 1 is 1 minus q, for omega naught is 1 minus p. Okay, omega naught is 1 minus p, omega 1 is 1 minus q. Let's go back to the first equation just one more time. Omega naught is 1 minus q and omega 1 is 1 minus p. Beautiful. Whatever is associated with whom. So just checked if there is anything else. Omega naught is 1 minus p, omega 1 is 1 minus q. Very simple. Now an example, MarkovSwitch model of the business cycle. A MarkovSwitch model of the business cycle is specified where P is when expansionary phase of business cycle is captured and Q is when contractionary phase of the business cycle is captured. So using quarterly percentage growth of United States GNP, the log likelihood function is maximized with respect to theta with the parameter estimates reported in table 19.4 whatever to ensure that the conditional probabilities P and Q are in the unit interval. This parameter restricted using the logistic transformation. Okay, exponential of lambda and I think eta. Now we maximize with unknown parameters, these two are coming from the exponential function, is added in the unknown parameters. Now which are terms coming from P and Q actually, so if we find them, we find P and Q, lambda and I am not sure what that is, K. The unrestricted parameter estimates are then obtained by maximizing with respect to the unknown parameters using one more iteration. The average growth rate in the business cycle is now 1.177% compared to average growth rate in the contractionary phase. So we have been able to concentrate out how much growth rate we find in contractionary phase, how much variance is in the contractionary period, how much growth rate is in the expansionary period, even how longer is the contractionary period compared to the expansion period, and estimate of the is respectively. So beautiful, right? We just need to find a lot of information. First of all, this allows us to find the duration of both the two different periods. It allows us to find estimates for each different periods, right? So that is quite interesting, and let's move forward from here. My apologies. So the terms separating out P and Q are kappa and lambda. So kappa and lambda are the new unknown parameters instead of P and Q, and finding kappa and lambda means you maximize the equation with P and Q. So let's see an application. Okay. Now let's talk about a MarkovSwitch model of the business cycle. I'm very excited with this model. I remembered that back in 2014 and 13, when I was working on some papers, I wanted to bring in the concept of MarkovSwitch models, which was quite big that time. However, I could not because due to limited programming abilities and the regular software like eViews and did not have Markov switches available or incorporated in some of the student versions that time. This time we're gonna try the best way possible, which is the programming way that allows us to look into each step separately so we know what's going on inside. So here we have a data file of 136 quarterly data on unit test as GNP. So we have 136 quarterly observation, and the model that we are considering is the regular model that we are familiar with, where dependent is the quarterly percentage growth rate in output, that is our Y, percentage growth rate in output. Omega is stochastic binary variable. Omega is representing the business cycles. This can represent crises and anything. U is disturbance and theta are the unknown that we know. So we need to estimate the unknown parameter theta by maximum likelihood and interpret the parameter estimates. So we need to estimate this parameter with MLE. We need to compare these estimates to the values reported wherever. A measure of duration of an expansion is given. We know the measure of the duration, 1 minus P. Contraction is 1 minus Q. So generally it is good to remember though, a measure of expansion is simply 1 by 1 minus P, whereas a measure of contraction is 1 by 1 minus Q. Basically these may separate out, if you are working on equity markets, this may separate out bubbles and non-bubble period. Estimate the duration of the two phases of the business cycle together with the standard errors. So we want to estimate the duration together with the standard errors, that's all. So we want to do the restriction where omega is 0. A potential test of Markov switch is based on joint restriction. We know that, we have studied that before. Well, beta and delta both are 0. So restriction is when omega 0, they automatically become 0. When omega 1, the mean and the variance we can estimate. So, and without the restriction, we can allow the system the model by allowing conditional probabilities to be time varying function of unemployment rate. So we are allowing the system to have another additional factor, unemployment rate. Very interesting and very nice, very beautiful. We're allowing the system to have an additional variable, which is unemployment rate, and that is simply including that with the kappas and lambdas in the denominator. So now we have to we need to do an LR test of time variant transitional probabilities by testing the joint restriction whether kappa and lambdas are zeros or no's, because remember, if your kappas and lambdas are zero, which will render your p equals 0, that means beta and delta automatically 0, and you don't need to do it separately. If your kappa and lambdas are non-zero, then you have values for q. So that is something that we talked about, and let's get back to our discussion, which was, I think, I just took a hunch. No, my hunch was wrong. We have covered up quite a lot of stuff from this chapter. So here, so we have the functions, the omegas. We are just watching how the log likelihood function is constructed, and using these matrix multiplication, we do a propagation forward, or we forecast our next omega and omega weighing functions. So given p and q currently, we can forecast given weighing functions before, we are estimating current weighing functions. Given the current weighing functions, we are estimating the future weighing functions. So that gives you a station time series model, which allows us to forecast and make predictions on what will be the next weighing function, and then jack them together. So finally we have this representing omega 1 and omega naught, and expansion and contraction is, so 1 minus p inverse is expansion, 1 minus q inverse is contraction, if I am correct. So 25, let's go back to page 40. Yeah, 1 minus p is expansion, 1 minus q is contraction. Let's go back to 25. Okay, let's do the problem now, solve the problem. Obviously we'll gonna do maximum likelihood, and we're gonna do LR test. So there will be two local functions that will be generated, and the local functions are restricted and unrestricted parameters. We are not gonna simulate any data, we're just gonna use given data. So the first things first is to do a restricted log likelihood function, and we call it log likelihood function. Restricted, we have b, y, beta, our parameters, y dependent variable, and flags. Depending on flag, stuff will change inside. So alpha, beta, we're suggesting who will take what place. Gamma, what are our unknown parameters? We have alpha, beta, gamma, delta. More, we also have p and q, but because we are talking about restricted, we are allowing the system to take on something, p and q. Because we are talking about restricted, we might not do kappa and lambda, but if we're in an unrestricted model, we expand the maximum likelihood estimation for kappa and lambda. That's the only difference. So if there is flag, then p, which is simply 1 divided by 1 plus exponential of this, and 1 plus exponential. So just if you are not sure about it, 1 plus exponential, you might ask where is it coming from. We have defined that earlier, right? Yeah, so exponential function, so 1 plus exponential of kappa and 1 plus exponential of 1 divided by 1 plus exponential of p and 1 plus exponential of q. Basically that's coming from, sorry, let me allow you to, coming from this part of the equation. And p and q are 0 and 1. We're going to ensure that this thing ensures p and q 0 and 1 if they are flags. If they are not flags, we'll have values for p and q estimated by MLE. So if we restrict, we fix it for 0 and 1, p and q, that allows us to find this. I mean, this ensures p and q 0 and 1. 1 by exponential of minus b5, 1 by 1 plus exponential of minus b6. Otherwise, we will have values. So there comes one if logical function. So if we have flag calling, then this portion of the equation will ensure p and q taking 0 and 1. Otherwise, we'll get values. So let's define the mean variances. The mean, okay, so row bind. See, column bind is things in columns, and whenever, so this one and this one are 2 columns, right? We do row bind. If they were in rows, we do column bind. Why? Because we're bringing the columns one after the other. So I'm just comparing R and MATLAB codes. And if we want variables to be represented in different columns, we basically bind them by rows. So row bind, very simple. So mean is for if they are, that is, we know if weighing function is 1, then mean is alpha plus beta, which is well, the first 2 parameters for mean. For variance, we have gamma and delta added together if wing is equals 1. Otherwise, if wing equals 0, the second term turns to 0. We know it already. Then we standardize. We have the mean, and so let's standardize. I think we have the variance too. Okay, y minus mu divided by square root of s2. Variance is there. Square root of s2, y minus mu divided by square root. So standardized variables. Standardized variables allows us to merge them together. Standardization is important. We can do z-score as well. Otherwise, this is a good thing. We can do z-score on, you know, m and s2. Otherwise, we can do this. This is the safest way. It gives us more control. Y minus m1 square root of s2 element 1 minus m2 square root s2. So distribution for sets 1 and 0. So now as we have standardized, we want to see is distribution, their distribution too. We want to separate out their distribution. So they are because we want to separate out f1 and f0. So normal probability distribution of z1 divided by square root, normal probability distribution of z0 divided by square root. Very simple, straightforward way to find distribution for 2 different states. Okay, simple, very simple. Normal probability distribution, norm PDF is expressed in R with dnorm function. The function is dnorm. So that is done only on z1. Then we divide with the variance again. We normalize it further. So what did we do up until now? We defined in the function we defined our variables. We found the mean and variances, use them to find normal distribution. Then we further we standardized them. Then we found normal distributions, further normal distributions, and normalize the distributions further by dividing them with the variances. So we are moving as many variances out from the system as possible. Then we are gonna define transitional and stationary probabilities, which is, as we know, for weighing function 1 it was 1 minus q by 2 minus p minus q, and 1 minus p, 2 minus p minus q. If you cannot recall, we can just go back and show it to you. So 2 minus p minus q, 2 minus p minus q. So 0, 1 minus p, 1, 1 minus q. So we'll start with 1. We are doing, the sequence is maintained, 1 and 0, 1 and 0 in all cases. So if wing function is 1, then 1 minus q and 1 minus p. Beautiful. Okay, so these are the stationary probabilities, where they become stationary. What is happening here? Again, we want them in different columns. We are calling them in the row bind function in R. Now it's time to do the likelihood function, and the likelihood function is very simple. You know, omega 1 function 1, omega 2 function 2. We already know, we have already found the function omega and the functions. Okay, here we have already found them out, and we could have done the hard way that was shown for our functions, but we found a much easier way to find our functions. Instead of doing the hard way, we just allowed our programming functions to find that those two functions for us, which is a very strong learning today. Basically, such, I mean, functions can be represented with this. If we have this, see, this was the last element, right? Just the last element, which is a normal probability density function. That's all. That's something we need to remember. Divided by variance. Good. So this is the equation. We are not thinking about the for loop yet. So if there is flag, then P will be this, as we know. Otherwise, P will be B5, B6, and this will actually go in. These P's will go in here. That will change the elements within W automatically. So when we call for a flag, then the P trans changes. Okay, so when we call for flag, then the P changes here. P trans is P1 minus Q. This is the, where is the equation? Oh no, it is transitional probability. Transitional probability is on P. That was transitional and stationary. That was stationary probability. This is transitional probability. Very important. Transitional probability. Okay, so if there is the transitional probability, we're doing it matrix, as we know. So if flag, this is the P, otherwise this is P, and we have transitional probabilities here. So we have conditional distribution, and then we update the weights, which is W1 F1 divided by Fi, W2 F1 F0 divided by Fi. By division, let me see. Okay. And then it is transitional probability multiplied to this. Okay, so W1 F1 divided by this, W0 F0 divided by this, multiplied to the transitional probability. Conditional, so we have two types of probability, stationary and transitional. F1 divided by Fi. Fi is this equation, the main equation down here. All right. Okay, so what we are doing here, we first find the stationary probability, then we are gonna construct a likelihood and find the transitional probability from it. So we put those first in a for loop up until 1 to t. So first we define the denominator, for the transitional probability. So if we call for a flag, as we know, P and Q will change. If we do not call for a flag, there will be different values P and Q. That assumes whatever it is, it will construct the transitional probability matrix, and then again we do row bind here, and then simply we multiply. We do row bind and we simply multiply, construct this equation for W1 and W0, right? So we have W's, omegas, basically, and that's it, and negative log likelihood function. The system will return the negative log likelihood function, okay, and all this defined. The system with BY flag, this will estimate everything for us. So this is one restricted log likelihood function. Unrestricted will take more parameters, estimate more parameters for us, which is kappa and lambda. Again, mean variance. First we find mean variance, then we find the standard. We standardize very simply. We use the standardized variable for different estimates, 0 and 1, and then we find the function, distribution function, the last element of the log likelihood function, and then we do stationary probabilities. Then we construct the likelihood with the denominator of the transitional probability. But here we change P and Q slightly, because previously P and Q was dependent on flags. Here P and Q is not dependent on flags. Rather, P and Q is estimated with this additional element. Okay, the additional element that represents unemployment rate, which is amazing. So unemployment rate is something that we input this time, give as an input, pass as an input. So it takes in the unemployment rate, and it estimates the transitional probabilities, and then we update the weight and we get expansion and contraction. So basically we find the log likelihood function with this, and we have everything. Actually the system gives us P, Q and everything that we need. Beautiful, 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 and very, very simple. The whole thing lies within understanding the theory here in MarkovSwitch model. And so this is just percentage growth, t length y, passing in the information that we have. We already have GNP and unemployment rate. Beautiful. Graph, fine, it's not a big deal. Then without the time varying parameter, we want first to estimate everything without the time varying parameter, estimate the model. We initialize, right, and kappa and lambda to control for time variant in the conditional probability. And let's do some initialization, some initial values. We pass in some initial values, which we will understand if we go to the question itself. No, not point 40. So let me see if we have any questions from where we are getting the initial values. Table 19.4 and in Hamilton. Basically this paper has the initial values that they are suggesting, or we can go to table 19.4. Somewhere around here there is a table that I don't remember at all where it is. This might not be that far. Okay, let me find the table out first. Basically it's not given anywhere, we're just estimating. You see this estimation initializing with random values, and see what we did here, starting with 0.5, then 1, 1.5, 1, 2, 2 is just nothing. Okay, how many parameters we are estimating? Alpha, beta, gamma, delta, p and q. Alpha, beta, gamma, delta, p and q. Okay, not kappa and lambda yet. So we call for fn insert. We know whenever there is a flag passed, we use for minimization, we use fm insert. But in R, that is the beauty, you don't need to do anything, just optim, call in the function optim. So par function, y, whatever the things that we need, y equals y, flag equals true, something, this is the tweaking part, new part. Okay, flag equals true. That is what is setting the difference between the regular optimization and not regular optimization. Beautiful, right? So y equals y, where this system will return us y, take y in as the data. Flag equals true, method bfg is. So, and by1, the whole function here, calling in the whole function here, but no commas in between. Beautiful. So we have theta parameters and the log likelihood function, and then we remove this clear start. I think we remove the effect of the optimization with clear start, and we have log likelihood function. Well, it's not that important, and something we don't need to do, at all, because we haven't done that in R. That is the beauty of comparing two programs together. Then now we need to estimate the model again to get standard errors based on Hessian. So we do start. We start here. We cleared the start, and we start with the estimated theta. Then we allow the system to take in 1, 2, 3, 4, 5 and 6, p and q, right? Start 5 and start 6, only these two elements, which equal to this. We solve this equation with initializing with these two elements. We're clearing the start because otherwise we'll take the optimized value, or just simple, we are doing it too much, the whole thing might not be required. So estimate the model again. So let's start with theta, c, updated parameter, and we take the fifth element. You see, the fifth element is 2, but it has been replaced with the estimated values. We take the estimated values to oh no, sorry, my mistake. We are estimating 5 and 6 by given by estimated fifth and sixth element. So 1 divided by, beautiful. So we are estimating the initial values, then we are calling the regular maximization. There is no flag here, minimization. So theta and Hessian is something we need. So again, the restricted model, neg log R startups. So flag is false this time. See, flag is false, not true. This is an optional command that we can, optional element of a function command that we can always pass in, but this time Hessian is true, right? So theta and Hessian, and variance covariance. From that Hessian we do variance covariance 1 by t inverse of Hessian, or the identity matrix, or minus identity matrix, and square root of diagonal of variance covariance is standard error. So now we have standard error. So you have MarkovSwitch model parameters. Okay, matrix C, theta, blah blah blah. I'm not sure what happened here. Okay, this is a matrix that is being created. Whatever. So MarkovSwitch model, alpha, beta, gamma, delta, everything is being prepared in list. It is gonna show me in list. Oh, this is just display, print, not a big deal. Gamma, delta, p and q. Beautiful. And we keep doing this clear start thing anyway. Now duration estimate is 1 by 1 minus p, 1 by 1 minus q. However, there is this thing, standard error for the duration of p only is square root of vc divided by 1 minus p square. Square root of vc divided by 1. This is something new that we learned. These two, square root of variance covariance matrix with the fifth element divided by 1 minus p square in both cases. Okay, not q, just 1 minus p square. In both cases we are doing 1 minus p square. So this is something new. We have to remember that this part. So duration for state 1 and state 0, very important, and the standard errors in these two states. Beautiful. Then we do word test, which is variance square divided by 4 by 4, vc 4 by 4, square matrix, theta divided by variance covariance matrix, 4 rows and 4 columns. We're taking the first 4 elements, basically. That is what I'm trying to say. The fourth element, just the fourth element probably, yeah. And now estimate the model again with the time varying probability, right? Now this is a bit of more fun. Now initialize. Before we did without, and we estimated what, theta c, right? Now we use these parameters that we estimated controlling. Basically we're gonna use without whatever we estimated without the time varying probability. Whatever we estimated without the time varying probability, we're gonna use that as our initial value, as our initial element, right? We're gonna initialize our with that, with all the elements from there, and we have additional 2 elements, 0 0, and we allow the system to find your unemployment rate. I mean, take an input of unemployment rate. Then we update 5 and 6 elements again. Simple, and then we do log ratio test. So you see, the beauty here is that why do we do 2 elements? What is the difference between restricted and unrestricted? First of all, in restricted we do flags. It allows us to call for a flag. We just develop a flexible system, okay? And there is more. In unrestricted we don't have kappa and lambda, so we are not allowing for additional elements to be added or to have effect on our output growth dependent variable. And the restricted model that we estimate before, that works as our initial value, okay? So we initialize given that value for our unrestricted parameter, which has the kappa and lambda now, and also the unemployment rate, which is very important. Beautiful. And we have also learned to find the duration, not only duration but also the standard errors of the durations for both cases. Beautiful. Display list. Okay, matrix theta at one dimension, name list, row name c theta. Oh, this is just, you know, making a list and displaying the whole list and showing that in matrix. Okay, yes, same thing. So that was fairly easy compared to what I expected. Has a lot of lines of code, obviously, because there is a lot of confusion with where to put restriction. But you see, 3 situations. You find PQ with flag, with the equation. Without flag, we let the system estimate P and Q, and whatever value that gives you, take it. We generally not do that, but we allow the system to have that flexibility. Then we do restricted estimation, unrestricted estimation. I mean, we define our equations. We also learned that the last element of our log likelihood function is simply normal probability density function. We use them actually, and beautifully we find wing functions, the matrix that gives us wing functions for both of the restricted and unrestricted log likelihood functions. Then we jack all these together. In first we do unrestricted estimation, we run the unrestricted optimization. When we do that, we don't find kappa and lambda. Okay, without kappa and lambda, with a random initial numbers, we allow the system to give us estimates, Hessian center, everything, and contraction and expansion period. Now we make use of the estimates that we find in this phase, and we use it in the next phase for unrestricted parameter with kappa and lambda and the additional impact coming from unemployment rate. We update that program, earlier program, by including these as initial estimates, and the whole system allows us to further estimate the 5th and the 6th, the kappa and lambda element. Basically, and now as we run this function, we update P and Q. So P and Q is not as before, it will not have the same P and Q. You see, because what we are estimating is either gamma and delta, like here, gamma and delta, sorry, not gamma and delta, okay, P and Q. No, let's go back to the, give me a second, let's get back to, no, I am in the right equation, right page, I guess. Okay, 1 divided by 1 plus exponential of anyway, what I mean to say here is that, well, let me just, give me 1 second, allow me 1 second, just, yes, let me see. No, what I am trying to say that we update P and Q after we do the estimation. That is something we need to remember in both cases. The estimation indeed gives us P and Q, but we don't use that. We update the P and Q for our 5th and 6th element in both cases. That gives us the new P and Q. Okay, so that is all in a nutshell for Markov switch. Thank you, and we'll move into the next example from here.